What we did discuss last class period was that there are different symbols for different things. We have a population parameter and we have a sample statistic. So whenever it comes to the population, you are going to use a capital N to represent the population size. But when it comes to a sample, we use a lowercase n. One other little tidbit is, for the most part on the AP exam or even on my tests, you're not necessarily writing the formulas out. You are either plugging in information and simplifying. I generally never recommend that you just write the formula just in case you end up using the wrong symbol. So for population proportion, it is a P with no hat for the population, and it is a P with a hat for the sample. So every time you actually collect data, so think back to our activity where you refreshed the page and you counted how many check marks out of 10 were, or how many cards out of 10 were checks, that is a P hat. But the overall 50-50 distribution is the P, the proportion of check marks. Something that we're not really going to use today, but just to kind of give you a point of reference, when it comes to means, and that is going to be quantitative data, it's going to be a mu for the population and an X bar for the sample. And just to kind of give you a refresher, proportions come from categorical data. So basically success fail questions. Do you have a dog? Yes or no. Do you have brown eyes? Yes or no. So things where you can sort people into categories, and means will always come from quantitative. And so that's going to be things like, how many AP classes are you taking? How long is your drive to school each day? Things where you would answer the question with a number. What we focus on today specifically is going to be going in and looking solely at proportions. So we're really not going to use the mu. We are, just because it's a mean symbol, but it's not in the terms of mean data. But our focus for this lesson, the next lesson, will be proportions, and then 5.3 will be solely for means. So all we're doing is P and P hat. Now, one thing that we did also kind of talk about was the fact that every single sample that you pulled, yes, there were some times where you had 3 check marks out of 10, 3 check marks out of 10, but those samples didn't always come in the exact same order. So because they didn't come in the exact same order, that was what we called sampling variability. And that's just a natural variation to your samples. You're not always going to get a perfect sample. I'm not going to flip a coin 10 times and always get 5 heads, 5 tails. There's going to be some variability to it, which is natural. And it's sometimes going to be skewed. Like for us, some people they refreshed their page and they had 10 check marks, which was the only time out of all 4 classes that happened. And so whenever that happens, it's not wrong. As long as your process is still random, that's all that matters. So knowing that, it's okay to have differences. So we're going to kind of refresh on all of the things we discussed. There were population distributions and sample distribution. So population is every single person, place, or thing in the population. So in this case, the numbers are slightly different than what we did. There was 140 successes and there were 260 failures. So this was like our check and this was our X cards. And so the population size for this particular situation was a total of 400. And then we had proportion of successes is just 140 over 400, which is 0.35. So this, and I know it's on the very far left, but I'm going to go ahead and rewrite it. This is our P. This is our population proportion. For the most part, when you read a question and you start getting information from what they're telling you, this P value, this ends up being given. They'll tell you 40% of people have brown eyes. And then that's just what you say. They're not going to necessarily give you a distribution like this. They're just going to tell you what the value is. There is only ever one population distribution because there's only one true value that exists out in the world. Now, when it comes to a sample, every single one of the 20 samples that you pulled technically has its own sample distribution. They have their own individual p-hats. So it looks like in this sample, they had 18 successes and they had 22 failures. So that means they took a total sample of 40. And all I have to do is take that 18 over 40, and that gives me 0.45. And so this is going to be your p-hat. So p is what is coming from the population. P-hat is what you are actually collecting from your data. So every single time you went in and counted how many check marks were there, that was a p-hat, a new p-hat. Yes, some of them had the same number, but it was still a new sample that came from random selection. There are very, very many sample distributions, and they vary depending on what you end up getting. So like for this one, when I have 40 things that I select, I could have 1 success, 39 failures, 2 success, 38 failures. All of those would be a different sample distribution. Now, these two things are not things that you will necessarily have to draw. You're not going to make bar graphs to represent your population or your sample. What's really, really important is knowing that P is from the population and p-hat is from a sample. That's kind of what we're getting on. Now, the big, big thing and the whole title of this unit overall is the sampling distribution. So I want to tell you, and I want it to be that it doesn't matter if you write sample or sampling. It really, really does, because we just worked with a sample distribution. That was one individual sample. What a sampling distribution does is it takes all possible p-hat values from every possible sample distribution. So think of all 20 of the trials that you ran. Every single one of those trials becomes, and I'm going to kind of just draw it on the sampling distribution we have, they get placed on a frequency, because at the very end of what we did, I combined all of our data together and we made it into a histogram represented by frequency. So the height that you're seeing is the frequency that each proportion occurs with. So all of the p-hats, all 20 that you made, would become a little dot, a little frequency on a histogram. And so what happens is it creates a individual sampling distribution for that specific sample size. There are a couple of symbols that we use. We have a mu of p-hat. That represents the mean of a sampling distribution. And then we have sigma p-hat. That represents a standard deviation of a sampling distribution. The big thing pointing out that this is a sampling distribution, not just a sample distribution. And we will eventually get to identifying the mean and standard deviation. I'm going to kind of take those as we discuss them in terms of like what we're going to learn today. But the big idea is that this sampling distribution is coming from all of the possible samples. Now, realistically, when you get a question, you're not going to have to make this. What you'll probably notice is this looks like it's a normal distribution. It looks unimodal, it looks symmetric, it has a center. We're going to calculate standard deviation. All of those things are true. So what we end up doing is we use a normal distribution for these problems. So once we go in, we have to make sure first that it is normal. And so that's kind of the big thing that we're doing today, is verifying through 3 conditions that this distribution is normal. What does its mean? What is its standard deviation? That is the only new thing that we're really doing with the process of answering these questions. So what we're going to kind of talk about, 3 conditions, and I have 3 kind of bullet points that we're going to discuss. The first thing we're going to look at is a center. So whenever we have a histogram, the center of the histogram typically is going to be the mean. If you have symmetric data, it is typically mean and standard deviation that gets talked about. If you have skewed data, it's median and IQR. A normal distribution is symmetric, so we're going to use the mean. Now, when we start taking samples of a population, we have to revisit the earlier question, how trustworthy is it? And so a sampling procedure that is biased favors a particular group of the population, and because of that, we don't want to use it. So if I go out and I take a convenience sample and I ask the first 20 kids that walk in the door, how long does it take you to drive to school? I may have a biased sample because maybe they got there earlier because their drive is longer. And so their parents have to drop them off earlier than they normally would. And so because of that, it's not representative of all RHS students. And so to avoid biased samples, we want to make sure that our sample uses random selection. Put little stars. This is very important, very key. One of the first things that we generally check for is there some form of randomness in our either sampling or our experiment? A statistic used to estimate a parameter is an unbiased estimator if the mean of its sampling distribution is equal to the value of the parameter. Basically what this means, if you have a number and it matches the center of your distribution, so say I have 0.5 for a coin and my center of my histogram is 0.5, that is unbiased because it matches directly with the population. And so if you have random selection, you are then able to go on and use the formula to find a mean. And so to find the mean of p hat, all we have to do is identify p. And remember, p is typically going to be given. They're going to tell you what they think the population proportion is. And so all you're doing in this first step, because there's 3, is verifying that they have random selection. So my little note for my people who are like, literally just tell me what to do and I will do it. Whenever you are trying to find the center, you just need to check for randomness. And if you check for randomness, you are then able to find mu of p hat. So if you do that, you can use that formula. And we will go through like how do you actually write this on your paper when we get to our example. Now for the second condition, because that's condition 1, the second thing that we're going to look at is for shape. So whenever we are doing this with the whole idea of it being normal, we want the shape to have a normal distribution. And so no matter what the shape is of the population could be skewed, it could be skewed left, skewed right, it could be normal. No matter what, the sampling distribution will always be approximately normal. As long as a condition called the large counts condition is satisfied. Now, if you get a question and they tell you originally that the distribution is normal, like the population distribution is normal, then yes, the sampling distribution naturally should be normal. But they sometimes give you a question and they'll say, the population is skewed. Can you assume that they have a normal distribution? And if it's skewed originally, as long as this condition is met, you can assume that the sampling distribution is going to be normal. So what we have to do is we have to take n times p and make sure that's greater than or equal to 10, and n times 1 minus p, and that's going to be greater than or equal to 10. What this is doing is this is basically making sure that you have enough successes and enough failures to ensure that there's going to be kind of an even distribution on either side of your histogram. Now, I will say, I know from what we've seen, I saw people working on MATLAB, there is a way that they write it on MATLAB. They do n times q is greater than or equal to 10, where q is just 1 minus p. So if you see that, it's the same rule. I think it's personally easier to see it as 1 minus p because then you're not asking yourself, what is q? So that's how I normally write it. But basically, you're just checking, do I have enough successes? Do I have enough failures? If both of these conditions are met, then we go on to say the sampling distribution is approximately normal. One little thing that they will be nitpicky on, you are never going to say that it is just normal. We will always use approximately. That's one of those things where I know I get my people who ask me, like, what is the word that I'm going to get points taken off of if I don't have it? If you don't have approximately normal, there will be points taken off. Now, in this case, just a little note, this is a result of something we call the central limit theorem. It's kind of like a branch of it. We don't necessarily call it this when it comes to proportions. We do refer to the central limit theorem when it comes to means because it is very, very dependent on that for means to kind of meet this category. So whenever you're doing this, you're checking these two conditions in order to say that it is normal. So for my people who just need a note of what do I actually have to do, this is going to be check large counts. So far, step 1, check if it's random. If it's random, you can use the formula to find the mean. Step 2, check if large counts is met. If large counts is met, you can say that the sampling distribution is approximately normal. And then the last thing, as I'm sure you've seen, we've talked about center, we've talked about shape. The last little bit is going to be your spread. Spread is how much variability you have in your distribution. And we represent that by standard deviation when our data is symmetric. So there is going to be variability in your graphs. There's going to be differences in how scaled your x-axis is. Sometimes the scale is really big, sometimes the scale is really small. And a lot of that depends on how big your sample is. Larger samples have less variability. So if I ask 10 people, how long is your drive to school? I could have numbers all over the place. I could have people who say, oh, my drive is like 1 minute. I live across the street. Or I can have people who say, I live in Lake Highlands, so my drive is like 30 minutes. So that could be a lot of spread between student 1 and student 10. However, if I ask 100 people how long your drive is to school, I'm going to get a lot of people who say the same thing. So I'm going to have a lot of frequency in like maybe 10 or 15 minutes. It takes me 5 or 10 minutes to get here. So whenever you have a bigger sample, there's less variability because you're going to have a lot more people who say the same thing because you're trying to represent the population and they are a part of the population. So the spread of a sampling distribution does not depend on the population size. It really, really depends on the sample size. And so just to kind of summarize that, because I know sometimes we don't always go back and look at our notes and actually read the words. As n goes up, your variability goes down. And you can even switch variability with spread, with standard deviation, whatever word they want to use to ask you. But as your sample size increases, your variability is decreasing. And that is a big, big idea with what they ask multiple choice wise. Okay, so for independent samples, and think of things that we do with replacement. So if I am rolling a die, or flipping a coin, or picking a card and then putting it back in the deck, that means that the proportion of successes is staying consistent. It's not changing at all. So if you know that something is independent, you don't really have to check anything other than saying flipping a coin is independent. So getting a heads isn't going to make the next one tails. So if you know that you have independence, you can go directly and use the formula. And these should P1 minus P all over N. These should seem familiar because we have used these. Like I said, you've done 75% of what we've done today. You've done this formula way back in September when we started normal distributions. You've used the formula for mean. You've used the formula for standard deviation. It's just now we're introducing it with questions that don't necessarily tell you The distribution is normal. It's something where you have to verify that it is normal before you can use it. Now, the issue then becomes, what do we do when we're sampling without replacement? So whenever we picked our 10 cards, we didn't necessarily put the cards back in the deck and pick another one. We just picked 10 out, and that was what we had. Now, when you pick something out of a deck of cards, we'll just use that as our example, that probability of success, that proportion of success changes, because now I don't have 50 cards in the deck. I have 49 or 48 or 47 or whatever you end up with when you get your number of successes. So I always kind of equate it to like sand on a beach, because this condition that we're going to eventually check to make sure that we can still use this formula is called the 10% condition. So basically, if I go to the beach and I get one little grain of sand and I take it home with me, that's not really changing the composition of what the beach is. It's the same. It's exactly the same. And so if I go to the beach and I get a bulldozer and I take 10% of all of the sand out of the beach, that is something that could potentially change what the beach is, the composition of it. It could create tide pools. It could create like new whatever. I'm not into beaches or sand, but whatever happens when you remove 10% of the sand. So what they say, and this is someone long ago decided that this was the threshold we were going to use, as long as you are not sampling more than 10% of the population, we're going to assume that the proportion is going to stay consistent. Think about it like if I am asking RHS students and I ask someone, how long is your drive to school? And I take them out of the sample, that doesn't necessarily really change the average a lot because my population is so much larger. And so what we have to do is within the 10% condition, you are verifying that we have sample size less than or equal to 10% of population size. And I will put that in words just so that my people who need to see it in words can kind of get a better idea. Sample size less than or equal to 10% population size. Now, the reason why we're spending so much time building these up is because these conditions are not things that they give you on the AP formula chart. You do get the formula for mean, you do get the formula for standard deviation, but there's nothing on there that tells you, have you checked randomness? Have you checked independence? Have you checked the large counts condition? Those are things where you're going to have to know going into it what to do. So one thing that I will say, a lot of the time with the population size, we don't really know the exact number. So we will usually put something that says, like, it's safe to assume that this is true. So if I'm trying to represent all adults and my sample size is 50, it's safe to assume there's at least 500 adults in the world. Now, when we use 10% condition and when we use independence, kind of varies. If you have something where you're doing an experiment, where you yourself are kind of changing things, so like flipping a coin, rolling a die, if you're just assigning 5 people to this medical study, you can't always assume that there is enough people to satisfy 10% condition or things. And so what we generally say in those cases is that they're independent of each other. So like patient A is independent of patient B, independent of patient C. And so if that's the case, if you have independence, you can just use the formula. If you don't have that, and usually when you are sampling from a population, you don't have that, that is when you check 10% condition. If all else fails and you're like, I don't know which one I'm supposed to do, because we will kind of go through both today, check 10% condition. And if it feels like it doesn't make sense, then just say they are independent, because one of those two things has to be true in order to find a standard deviation. So 3 things, 3 brand new things. We have randomness to get mean. We have large counts to check that it's normal. And then we have 10% condition to calculate a standard deviation. And 10% is just checking for independence. So let's go in, let's actually do some math. Now, I kind of did one problem with prompts. So showing you step by step what has to be on your paper. And then the second problem is going to be what you would be seeing on a test or on the AP exam. So first thing, let's pull some information from the question. A recent study looked at the percentage of young adult women. That is going to be my population, who get less than 7 hours of sleep at night. In this study, they say that 45% of women get less than 7 hours of sleep. So this is going to be the population proportion. This is what they think it should be. What is the probability that a random sample of 50 women, that's going to be my N, will result in a sample proportion of 50% or higher? So this is really what I'm trying to find. So a lot of the time I like to go in, and this isn't a necessary step, but I like to find from the question, what am I actually kind of baseline starting to look for? And I'm trying to find the probability that the sample proportion is greater than 50%. Now, in August, September, when we first started normal distribution, we would have just went in, we would have found a z-score, we would have put it in normal CDF, and we would have wrote our sentence to conclude. And we're going to do most of that. The only added step that we have here is that we have to verify it's a normal distribution first. So all of those questions you got back in August, they had something in the question that said, this can be represented by a normal distribution. And you didn't have to check conditions. But now we don't have that sentence anymore, so we have to check them. So I'm going to go in and first communicate the parameter. So I'm trying to estimate the proportion of women, young adult women who get less than 7 hours of sleep at night. Now, common abbreviations are completely okay. I did not write hours out completely. I wrote it as HRS, and that is fine. Mm-hmm. I mean, I think that would be acceptable. It's just like when you're like using all just letters of sentences. I think YA is fine. Okay, so step 1, done. Step 2, this is going to be where we go in and do the new stuff. We check the 3 conditions. A lot of the time, I like to, when I do this, because I will sometimes forget to check all of my conditions as well, I come in and I make bullet points. So I know I need to be checking, is it random? I know I need to be checking, is it normal? And I know I need to be checking, is it independent? And by doing this, this kind of ensures that you don't forget to do one of them, because all 3 have to be there on the AP exam to get full credit. When it comes to writing these out, the order you write them in does not matter. I do the same order every single time just because that's just what I do. But you could technically check for independence first and then do the normal and then do random. Or you could just write them all side by side. As long as they are on your paper, that is what matters. Truthfully, you don't even have to do this in this exact order. You could do all of the math and then be like, oh man, I forgot to check conditions. I'm going to check them off to the corner, and they would still give you credit on the AP exam. So as long as they are on your paper, that is what is going to matter. So in this case, if I read through what they have, they did tell me that it's a random sample of 50 women. And you do have to reiterate things that they say already. And I know for my people who do not want to write, this is heartbreaking, but you got to do it. Random sample of 50 women. And so if we have a random sample of 50 women, that means we can go ahead and calculate the mean. So I'm going to say mu of p hat is equal to, and they said that the population proportion that they think to be true is 0.45. So step 1, done. Step 2 is we are checking the large counts condition. So you don't always have to write the formula. I'm going to write it now just so we have a point of reference. N times P has to be greater than 10, and N times 1 minus P has to be greater than 10. And so what we do is we just fill in the values. Normally, I would not write this part at all. I would just go straight into filling in the numbers that I know. So I'm going to put... my sample size was 50. My P is 0.45. So that's 22.5, greater than or equal to 10. 50. I always just go ahead and do the subtraction. So 0.55 is 1 minus 0.45 is equal to 27.5. And that's greater than or equal to 10. If both of these things are true, then we can go on and say the sampling distribution is approximately normal. Yes?
So, I know you said that like approximately matters, but right now we're checking for normalness, so how is it like still?
The 10% condition doesn't verify that it is perfectly normal. It just verifies that it will eventually become more and more normal. So it's as your sample size starts to get larger and larger, it gets more and more normal. So that's why we always say it's approximately, because it's never perfectly normal. You will never say that it's normal, ever, ever. Because a normal distribution is technically one that is perfectly symmetrical on either side, and that doesn't always happen. Okay, second condition, done. I always get the question of, do I actually have to calculate the value? Everything I've seen in grading rubrics from FRQs is yes, you do have to plug in the numbers and you do have to show that it is bigger than 10. You can't just say like, yes, large counts is met and then move on. So plug in the values, simplify, show that they're bigger than 10. One little thing that I'll point out, both of those numbers that you get should add up to your sample size. So that's a quick and easy check of, do they both pass if you're doing something like multiple choice. The last thing that we have to do is independence. And so that was going in and verifying that N less than or equal to 10% of the population. And so for us, our sample size was 50, which is less than or equal to 10% of all young adult women. And so we'll just go on and we'll say that that is safe to assume. Sometimes there will be questions where they'll say there's 2,000 students who go to high school A, and then your sample is like 200 or 400 or something big. And that would mean you would need the high school to have 4,000 students in it. And that's when this condition would fail. For the most part, all of your conditions typically pass, especially if they're giving you a question on the AP exam. There's not going to be a question where one of the condition fails and you're supposed to stop. And they're like, oops, you kept going, gotcha. That's not going to happen. So if you happen to be on a test or on the AP exam and you're like, wow, this condition failed, should I just stop? Usually the answer is no. I would keep going, because most likely something happened in you checking the condition that made it wrong. Because they're not going to do something like that to you. I would think never. So to calculate the standard deviation of p hat is the square root of 0.45, 0.55 all over n, which is 50. And so that was 0.0704. And so the formulas that I'm plugging into are just the formulas that we wrote out prior to in those little condition checks. Both formulas, the mu of p hat equals p and the standard deviation of p hat equals 0.45, 0.55, all of those things are on the formula sheet. You don't have to memorize them. They are there. They will be there for both one proportion, two proportion, one mean, two mean, all of them. Okay, now back to some stuff that you already know how to do. So whether you remember or not, we did learn a z-score is represented by a value minus mean over a standard deviation. In symbols for what we're using, this would be something like p hat minus mu of p hat all over standard deviation of p hat. So in our case, for this particular question, they want to know what is the probability that it is 50% or higher. So I'm going to do z is equal to 0.5 minus my mean, which was 0.45, all over my standard deviation, 0.0704, in order to get my z-score, 7102. Not brand new information, hopefully. The next thing that we did when we got a z-score is we went straight to normal CDF. I will always recommend to use your calculator. Now, the one thing that I am approaching this as is if it were an FRQ. And so that means you have to calculate a z-score first. I know there are ways where we can adjust the mean and the standard deviation to match the problem, and it gives us the answer without calculating a z-score. And yes, that does work. However, they will not give you full credit on an FRQ. So normal CDF. And then I'm going to have, in this case, because I want it to be higher than the value that I have, my lower is actually going to be the z-score. My upper is going to be infinity. My mean is 0, and my standard deviation is 1. And it is always 0 and 1 when you are working with z-scores. The only time I would ever advise you to change that is if you are doing a multiple choice question, because they don't care what work you show on those, and you can just go ahead and say, this is the answer. Okay, now for my people who have forgotten, I'll kind of walk you through those steps really quickly. In my calculator, if I go to second vars, and vars is kind of right underneath the down arrow, option number 2 is going to say normal CDF. And yours should have like its own window that comes up that has prompts on it. And so I'm going to put 0.7102. If I wanted to put in infinity, I would actually type in 1e, and e is second comma, comma's right above 7, 1e 99. And then 0, and then 1, and then we get the probability 0.2388. So again, normal CDF is in second vars. Number 2, you are not using normal PDF. It's always normal CDF because it's always a cumulative function. So this is going to be 0.2388. And if you need reminders, normal CDF, second vars 2. And then infinity is 1e99. Now, unlike with probability where I told you you only have to write a sentence if they say to interpret, any of these open-ended FRQs that we're doing in Unit 5, Unit 6, Unit 7, they have to have a conclusion sentence. It's required. And we will have some later on that are like sentence stems that you're probably going to somewhat remember forever because we do it so much. But for now, I'm basically just going to repeat the question. The probability that a random sample of 50 women will result, I'm literally repeating the question, will result in a sample proportion of 50% or higher. And I still like to give it some context. So reading this sentence doesn't necessarily tell me anything about what I'm actually investigating. So I'm going to say who get less than 7 hours of sleep. Yes, Zoe. You can. I'm just following what they say. We'll do YA. Random sample of YA women. 7 hours of sleep is approximately 23.88%. My board is like behind me by 30 seconds. Now, before you think that your life is over because you have to write so much, there will, like always, be 2 FRQs on your test. So at the end of the day, you're probably doing this process twice, and that is it. So keep that in mind. On the AP exam, they usually ask you, and it probably won't be something directly like this because this is going to kind of lead you into inference testing a little bit, but you're really only writing like 2 or 3 summary sentences across your 6 FRQs. So I know it feels like a lot of writing just because we kind of were doing probability for so long and that was straight math. But a lot of what is happening in these later units is coming from your calculator and you're just interpreting it. And that's why they want you to write something summarizing what's going on. So now that we've done one and we broke it into pieces and took our time with it, let's do one where this is probably what something like you're going to see. So Egan, he was my victim. Egan fails to study for his AP Stats final. The final has 100 multiple choice questions, each with 5 answer choices. Assume all questions are independent and Egan has given himself over to the gods of chance and he is going to randomly guess on all 100 questions. What is the probability that Egan will get between a 25% and a 50% on the test? So what I'm really trying to find is the probability that his sample proportion is going to be between 0.25 and 0.50. What is that value going to be? And so just to kind of go through the steps that we've kind of already listed, my P is going to be the proportion of questions he gets right. And if it's helpful to you and you're like a spatial person and you like know, like you're blocking it in your mind already, you can always come in and say, okay, like that's my step 1. I'm done with that part. And then I like to go in and I like to check my conditions. I still, of course, always label everything first. I'm going to do random. I'm going to do normal. And I'm going to do independent. And these are going to look slightly different than what we did in the last problem, just because I wanted to show you examples where you don't always have to use 10% or you don't always have like random selection from a population. We are not selecting just a couple of questions and looking at that sample. We're looking at all 100. However, we do still have a random element, and he is randomly guessing on each question. So that is our element of randomness. Because sometimes you're randomly assigning treatments. Sometimes you're randomly selecting from the population. Sometimes you're rolling a die and randomly getting heads or tails. All of those things still meet this randomness condition. And so because of that, mu of p hat, if there are 5 answer choices, that means there's 1 correct answer out of all 5. And so we have a probability of 0.20. So condition 1. For normal, that is when we go in and we check large counts. So there are 100 questions. He has a 20% chance of getting it right. And there are an 80% chance of getting it wrong. And so since both of those are bigger than 10, we can say that the normal condition is met. The 10% condition is met. And so we can say the sampling distribution is approximately normal. And for the last condition, independence, they tell us in the question, all questions are independent. And so that's literally all I'm going to write. All questions are independent. Now, one thing I will point out, if you're someone who's like, I know I'm supposed to do 10% condition, and you forget this whole idea that you can just say they're independent, we don't have a sample size to use for the 10% condition. So as soon as you start to realize like, something funky is going on because I don't have what I need, go back and double check that it's not something where the things that you are looking at could be considered independent of each other. So I'm going to take my P, my 1 minus P, all over N. And that is going to give me 0.04. So I have my mean, I have the fact that it's normal, I have my standard deviation. That is all done. Now, the last little bit is going in and actually calculating my z-scores. I have 2 of them because I need to find a z-score for the 0.25, and I'm just using the mean and standard deviation that I just found, and I need to find a z-score for the 0.50. And so for the first one, if I plug it into my calculator, I get 1.25, which isn't very far from the center. Yes, it's a little bit on the right-hand side. It's a little above the mean. But when I go to this other one, the 0.5, I end up getting a z-score of 7.5. And if you remember anything about normal distributions, we had a rule called the 68, 95, 99.7 rule. So that meant 68% of our data was within 1 standard deviation, 95 was within 2, and 99.7 was within 3. So when you get z-scores like 7.5, which are way outside of 3, the likelihood of them happening is very, very low. So I'm going to go in z 7.5. You do, if you're doing this in your calculator, which most of you will be because we don't use the tables, you do have to write out normal CDF, and you do have to label your values. So 1.25 upper, 7.5. If you're using z-scores, it's always 0 and 1. Yeah.
Just the probability statement, or what not what's the probability statement? Does the thing on the
It's a probability statement.
does that have to be there to get points?
So if you wrote it up here, like you know how I wrote the one up there that is in the p hat showing direction,
Yeah.
that would be okay if you did not have it down here. But there has to be something showing I'm actually going in between these 2 values when I find my probability. So one or the other has to be there.
Okay.
It doesn't have to be like the orange one has to be down here, but something on your paper needs to be showing like what are you actually finding. And so this ends up being 0.1056. And that is step 3. The last thing we have to do is conclude, and that is going to be the probability Egan gets between a 25% and 50% on a 100 question AP Stats final is approximately 10.56%. Okay, so one little thing that I'm going to kind of mention before I set you off and you do your practice. Because a